So we're going to do some practice problems about radioactive decay. The first thing that we need to do is to have a periodic table. So this is obviously just Google. If you type periodic table of the elements into Google, you get this, which is a wonderful periodic table, perfectly useful. For example, if I wanted to know, how many protons are in silicon, I find the element silicon. There it is. So it's the symbol Si, and the 14 right here is the number of protons. That defines silicon, right? So say, any of you just point at any of these elements, right? There's nitrogen, right? Nitrogen has 7 protons. Oxygen has 8, and so forth, right? And any one of these. Here's lead. Oops, right there. There's lead. Pb has 82. All right. So now let's get to the actual problems that we're going to do. Okay. There it is. All right. So we talked about this in the PowerPoint. The stability of nuclei from elements 1 through 20. All right, so you look on the periodic table, elements 1 through 20. Here, let's go back. So element 20 right there is calcium. So elements from hydrogen to calcium, there should be a 1-to-1 ratio of neutrons to protons, right? So for example, potassium has 19 protons. So to get a stable isotope of potassium, you should have 19 neutrons as well, right? So that's the way it works, and then that works all the way up to calcium. Now beyond that, from element 21 all the way to element 83, 83 is bismuth. There is a range of stability, right? So here, let's take a look at that. And of course, anything beyond element 83, these other things like polonium and so forth, they're automatically radioactive, right? Like uranium is well beyond 83, and so that's automatically radioactive. In other words, there's no number of for elements beyond bismuth. There's no number of neutrons that can stabilize those very heavy nuclei. All right, so let's switch back to the problem. All right, so here's the range. All right, so from elements 21 through 83. The neutron to proton ratio. So you got to figure out the number of neutrons that the element has. The neutron to proton ratio has to be within anywhere from 1.5 to 1. So this is the range that I'm talking about. So that ratio has to be anywhere from 1.5 to 1 all the way down to 1.25 to 1. If it's within this range, then the element is very likely to be stable. Of course, you have to actually go and look. So here's a couple of little other things. And I just mentioned this: atoms with anything, any atomic number greater than, or the number of protons greater than 83, automatically unstable or automatically radioactive. And these sometimes these are called the magic numbers in nuclear physics. If the nucleon number, now nucleons of course are the number of protons and or the number of neutrons as well. So the number of neutrons and protons, if it's 2 or 8 or any of these numbers right here, that adds stability, right? And of course that has to do with this this pull and push between the strong nuclear force that's holding the nucleus together, and the electromagnetic force that only gets weaker over a large nuclei, very large nucleus. Basically when the strong nuclear force gets weakest, for these really large nuclei, then it just won't hold it together. It won't hold the nucleus together anymore. All right. All right. So I just did that. All right. So let's do some of these. So these are pretty simple. So silicon 28. All right. So let's look at silicon. And we'll see how many. So we got to figure out the number of protons, the number of neutrons, the neutron to proton ratio, and we're going to predict. All right, so we just look up on the periodic table. Silicon, of course, by definition, has 14 protons. But this is, in particular, this isotope is silicon 28. All right, so the number of neutrons, let's write this out, is going to be 28, right? Because that's the 28 is the number of nucleons, right? The number of protons plus neutrons minus 14, all right? So of course 28 minus 14, right? Minus the 14 protons gives us 14 neutrons, all right? And so the neutron to proton ratio, so it's, this column right here divided by this column. So it's going to be 14 divided by 14. Of course, that is equal to 1. And remember, for elements that are less than 20, and which of course element 14, which is silicon, is less than 20, it should have a ratio. So see where it says right here, the ratio should be 1 to 1, right? And that's exactly right for this one, right? So we're predicting that this one is stable. Right? This is stable. All right, so we'll just do it like that. All right, so the next one, our astatine 203. All right, so we need our periodic table. We got to find astatine. All right, let's see. Let's switch over to this. There's our periodic table. So astatine is, let's see, where is it? So astatine, as I was just saying, is right here. It's element 85, right? You just move the cursor and you can clearly see the name right there, astatine. So that's element 85. And so for the very first thing, we don't even have to do any calculations, but we'll do the calculations anyway. It has 85 protons, right? So we need to know that, right? So all right. So I've gone back to this worksheet. So there's the 85 protons. And then, of course, we have 203 minus 85 to get the number of neutrons. Now, we don't really need to do that anymore for this one. We'll do it just to show that what the ratio is. But we already know that this one's going to be radioactive, right? Radioactive. And the reason for that, is, and notice it says here to give our reasons. The first one, the reason was you have this the neutron to proton ratio of 1 to 1. This one, the reason that it's going to be radioactive automatically is that it's element 85. 85 is greater than 83, so that's automatically. All right, just speed this up a little bit. I filled out some of this stuff. So of course, here's the number of protons for astatine. The number of neutrons, you just take the nucleon number, subtract the number of protons, so it's 118. And so the ratio, remember, even though we don't have to figure this out, the ratio is 118 divided by 85. Now, notice that ratio is within the range, right? The range, it says it should be no greater than 1.5, but less than 1.2. I'm sorry. It's got to be between 1.5 and so less than 1.5, but greater than 1.25. And that's clearly the situation here, but that is not stable, right? It just is not stable at all. And one of the reasons, of course, as well is there's really two reasons. One is that this is radioactive. One is that it's element 85, so it's automatically radioactive because it's greater than 83. But also the fact that you have an odd number of protons that tends to lend itself towards being radioactive. All right, the next one, of course, is nickel. Nickel 56. So we got to look up nickel. All right. So here, let's go to this. All right. So nickel is right here. So nickel is element 28. All right. So it's great. Remember, that's going to be greater than 20. All right. So keep that in mind. So we're going to look for that ratio between 1.5 to 1.25. All right. So it's got to be somewhere in there. So let's see. So this is element 28, so that's really what we need to know from the periodic table. All right, let's go back to this. All right, so it's element 28. All right, and so the number of neutrons are going to be, since this is nickel 67, it's going to be 67 minus 28. All right, so that is going to equal. All right, so just to complete this, the nickel 67, of course, it just being nickel, it has 28 protons. So 67 minus 28, that's the number of neutrons, is going to be 39. And then the neutron to proton ratio is going to be 39 divided by 28. And so that's 1.39, or close to 1.4. So just from our little model, we would predict that that's stable. Although I know, our little model is not always perfect. It turns out that nickel 67 is radioactive, and the reason that it's radioactive. All right, so to answer this, we can just use that it's stable, right? That we can say that it's stable, but these predictions, you actually have to go and measure it. You have to use a Geiger counter and see if these things are stable or not. This one actually is not stable, and the reason is this odd number of neutrons. Remember, the nucleus likes to have even numbers of protons and even numbers of neutrons. All right, the next one, of course, is oxygen 24. All right, so let's take a look at that. So we got to go to our periodic table, look at oxygen. Oxygen is element 8. All right, so let's go back here. So that's going to be element 8. And then our number of neutrons is 24 minus 8. All right. And of course, that's going to equal. All right, so this isotope of oxygen, oxygen 24, will have 24 minus 8, 16 neutrons. So right away, you don't even have to do this ratio. You already kind of see. You always do the ratio to make sure that the number of neutrons to protons is correct. But for oxygen, which is element 8, remember, we go up here, element 8 is between 1 and 20, and so its ratio should be 1. And it's clearly not. The ratio is 2. This is a highly radioactive isotope. All right, so we look up iridium 197. Well, we just look up iridium. We find that it's element 77. So to get the number of neutrons, it's this isotope is iridium 197. So 197 minus 77, 120 neutrons. So 120 divided by 77, right, is 1.558, something like 1.56, or you could round it to 1.6, right? So that, if you remember, it's got to be between 1.5 all the way down to 1.25, right? So that this is too big, right? So this we're going to say is radioactive. Active. Sorry. This one's going to be. We're going to predict that it's radioactive. As well, you can see, of course, it has an odd number of protons, which lends itself. That doesn't, that by itself doesn't mean it's radioactive, but that